Okay, so we're in chapter 8. We're going to talk about area and volume, applications of integration. So consider the following triangle. Say this triangle is 5 inches high and 10 inches wide. No matter what kind of triangle it is, a isosceles, a cube, whatever. It doesn't have to look like that necessarily. But the height is 5 inches and the base is 10 inches. And of course, you know how to get the area, right? Well, how do you do it? For any triangle, forget integrals. So the base is 10, the height is 5, 1/2 base times height is 25. Done, right? Okay, I'm going to be obtuse on purpose. How do you find the area of the triangle? You use Riemann rectangles. Remember Riemann? Left sum, right sum, right? We're going to make a Riemann argument here. I'm going to say, okay, I don't know, let's say I don't know how to do the area of a triangle. But again, I do know how to get the area of a rectangle. Now pretend it's infinitesimally thin, right? Right now it's delta y in thickness, let's say. Okay? Let's say that the thickness of this thing is delta y. What I want is for delta y to go to 0, so I have infinitely many rectangles, and I don't have this error. See this gap here? I'm losing some area. I get that error to go to 0 as delta y goes to 0, right? Just like left sum, right sum, that stuff. Okay. Let me call this length here, let's call this x. Okay? Let's call this height here, let's call this height y. No. Okay? Now my question is, what is the area of that one rectangle? That's all I want. Based on the area of the rectangle, you can get the area and volume of anything. That's the point today. Okay? So I'm going to say, what's delta A? My Riemann statement is the area of that rectangle. How do you get the area of any rectangle? Base times height, the length times width. Let's say the base is delta y and the height is x, like that. Okay, so base times height. Whoops, that's the height. Okay, great. But what I'm going to do is I'm going to add up all these delta A's. I'm going to add up infinitely many rectangles. They're infinitesimally thin. And to do that, I'm really going to integrate, right? Remember that big integral symbol is just the sum of all those rectangles, right? That integral symbol is an S for summing all those rectangles. So can I integrate x dy? Can I do that? I can't do that. So is there a relationship between x and y? So I can get rid of x, rewrite it in terms of y. Well, notice that these two triangles are similar. See this little triangle up here? And the big humongous one? This is parallel to this, otherwise forget about it. So this is a similar triangle to this. So how do I get x? Well, base is to base. Base of the little triangle is the base of the big triangle, as height is the height. Height of the little triangle is height of the big triangle. There's a proportion, similar triangles have their sides are in proportion, right? But what's the height of the little triangle? How much is this? What? 5 minus y. Okay, 5 minus y. Okay. So if I say base is to base of the little is to base of the big, as height is the height, height of the little is the height of the big, I could find an expression for x in terms of y. How do I get x alone? How do you get rid of this? It's not the toughest question they asked all summer. How do you get rid of the 10? Multiply. What's 10 fifths? 2. Can you distribute that? X equals what? 10 minus 2y. So I'm going to rewrite my Riemann statement in terms of just one variable. 10 minus 2y delta y. Now that I have in terms of all one variable, I can then say, okay, let's take the limit. As delta y goes to 0, then delta a becomes a, the integral of this mess. From what to what? How are the y's varying? From what to what? 0 to 5. All right, so let's get that area. How do you antidifferentiate 10 minus 2y dy? You get 10y minus y squared, evaluated from 0 to 5. So plug in 5, and you get 50 minus 25 minus plug in 0. Well, 0 minus 0, isn't it? So don't you get 25 square inches? Which is what we said in the first place, 1/2 base times height. 1/2, 10 times 5 is 25, right? But this is the hard way to do it, right? Not really. This is going to allow you to find the area and pretty soon the volume of a lot of weird shapes that you wouldn't otherwise know how to do. So if you think of it this way, with a Riemann argument, this was made up by Riemann, came up with this stuff, okay? You start with a Riemann argument, you're in good shape. All right, this is what you got to do. All right, any questions on that first example? How you get an area? Actually, applications to geometry. All right. Well, wait a minute. That wasn't really the question I had in mind. What I really wanted was, this is the cross section of a cone. I want a volume. Think of this like revolved around its axis of symmetry. Think of a cone. Could you get the volume of the cone in a similar fashion? Let's see. Let's take a look at this cone. Same dimensions. All right, but it's not a triangle now. It's a cone. So instead of taking a slice, which is a rectangle, I'm going to take a slice, which is a little cylinder. Think of like a coin, like a dime, right? It's very, very thin, and it's got a circular face, right? So one of these really, really thin slices, like dimes, okay? Can you make a similar argument? Can you make a Riemann argument for delta V, the volume of that cylinder? Can you use the volume of a cylinder to figure out the volume of a cone? Yeah. Because again, I'm going to call this thickness what? Delta Y. And as delta Y goes to 0, the thickness goes to 0, this gap here, this volume I'm missing will go away. So if we can get the volume of one of them and add them all up, I get the volume of the whole cone. But remember, the relationships are still the same. This is still 10 inches. This is still 5 inches. I'm still going to call this x, the diameter, x. So I'm going to say this is y, and this is 5 minus y. The same stuff. What's the relationship between x and y? Do we need a relationship between x and y this time? Maybe I'm jumping the gun. How do you get the volume of a cylinder? Let's start there. How do you get the volume of a cylinder? This is like a Coke can that's squished, flat. Okay? That's what it is. It's still a cylinder, has a certain thickness, which is very, 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 very thin. Okay? So how do you get the volume of a cylinder? Any ideas? Right, it's the area of the face, which is a circle. How do you get the area of a circle? Pi r squared times the thickness. All right, so it's pi r squared times the thickness. But what's r? If this is x, like before, what's the radius? If this whole thing is x, right? The radius is what? 1/2 of that. Remember we said the area of the face is pi r squared times the thickness. Okay, good. That is a statement for the volume of that one little slice. That one little slice. Think of this cone like a piece of cheese, and you're slicing out that little slice there. Okay? That's the volume of it. But again, think of it. I'm going to take the limit as delta y goes to 0, so I can end up integrating. So I add up all these volumes as these delta y's go to 0. I get zillions, infinitely many volumes. Add them all up. I'm going to get the volume of the cone. So I do really need this in terms of y, because I can't integrate dy on x. I can integrate dy on y. But remember the relationship. X is to... Don't you still have a cross section of similar triangles? X is to 10 as 5 minus y. This is to 5, right? It's the same relationship. Just if you slice right down the middle of this thing, you get this cross section. Same relationship for x and y. So if x is to 10 as um, the base of the small is to the base of the large as the height of the small is to the height of the large. Again, you get that x is 2 times that, right? But I want x over 2, and then I want to square it. What's x over 2? Nah, 10 minus 1, careful. Almost. 5 minus 1, right? It's like distribution. I divide both by 2. So I get delta v is pi times 5 minus y squared, because x over 2 is 5 minus y, and I'm squaring it because that's the radius, delta y. This is all in terms of y. So v is the integral from 0 to 5 again, right? Isn't the y values, if you think of this as the base being 0, going from 0 to 5, okay, of pi r squared dy. And now you can do it. Okay. How do you integrate that? Let's put this on the next page. I'm running out of room. Let's put this next page. V is pi, the integral from 0 to 5 of 5 minus y squared dy. How do you do this antiderivative in here? Any ideas? You can do it. U sub. You could do U sub, or you could FOIL it out, right? Let's do U sub. U is. All right, so let's do the indefinite integral right here. Forget the 5 and the 0, just this much, right? A little scratch work over here. If U is 5 minus y, du is negative dy. So I'm going to replace dy with negative du, the integral of u squared, yes? So what do you get? How do you integrate u squared du? You get u cubed over 3, and it's negative plus c, all right? But u is, okay, so I get negative quantity 5 minus y cubed over 3 plus c. Everybody okay with that? That's the antiderivative. So I'm going to say equals pi, how about negative pi, times 5 minus y cubed over 3 evaluated from 0 to 5. Okay. Equals negative pi times, let's see, if we plug in 5, what 5 for y, what do you get? 0. You get 0 minus, plug in 0, you get 125, 5 cubed over 3. All right. What's a negative times a negative? Well, 0 minus stuff is just negative stuff, right? So what's negative times negative? Positive. So you get 125 thirds of pi cubic inches. Remember, we started off with inches, right? And if you want a decimal equivalent of that, it's, I don't have it. I thought I had it. Hang on. Let's bring up our calculating device just for fun. It's always nice to have a decimal equivalent. Go away. There. Okay. No, not you. Stupid thing. Hang on. That's right. Okay. So remember, no right clicks. Okay. Forget, no right clicks. Okay, so 125 over 3 is that, but I want times pi, right? So times pi, just if you want a decimal equivalent, or if you want to check with fint, you get that 130 point, if you round that off to 3 places, what do you write? Point what? If you round that off to 3 places, it's 0.900, right? Yeah. All right, so I'm going to go back to, where the heck was I? So that's approximately, the freak was it? 130.900, okay. So 130.900 cubic inches. I'm still going to write 900, showing that I'm rounding off to 3 places, even though I have zeros in it. right, so if you want a decimal equivalent, that's fine. An exact answer is always good. That's fine too. Don't forget units. When there's units in the question, there should be units in the answer. And so we did some area, we did some volume. Both the same way, using a Riemann statement. You got to set up the area or the volume of one small slice. Then you're in business. That's the game. All day tonight. Okay, all night. Okay, any questions about that? We good so far? So good? Alrighty. So let's try another area question. Let's try this again. Let's practice this up. All right, say I want the area of this semicircle. Yeah, pretend it's a semicircle, okay? It has a base of 14 inches. How are you going to get the area of that semicircle? I know, you know the area of any circle is pi r squared, and r is 7, so pi r squared would be, what's 7 squared? 49 pi, right? And it's a semicircle, so divided by 2. So 49 pi over 2. I know the answer. That's not the point. The point is, can you set up a Riemann statement to get the same answer? Can you get a Riemann statement that works here? All right, I'm going to do the same thing. Remember, we only really know, pretend, that we only really know how to get the area of a rectangle. Remember, this is area, right? Not volume. We're doing area, we're talking about rectangles. When we do volume, we're talking about little cylinders, okay? So how about if I do just like I did with the triangle? I'm going to make a little rectangle here. Thickness delta y. And it doesn't have to be delta y and x all the time. It could be s and delta h or something, whatever the heck you want. Okay? So, what if, just like before, I call this whole side of the rectangle, I call that x. Can you give me a Riemann statement for the area of that rectangle? Based on time, what do you get? X times delta y, right? Just like before. Is this new? Look, that's exactly what we said over here. X times delta y. Same statement. Okay, that's good. But x and y are related differently now. Is there a way to write x in terms of y so I can get rid of x like I did last time? All right, now notice this is 14. So what's the radius? 7. What if I call this much, how high the rectangle is from the, say, the ground? Y. And this much here, yeah, this much here is just the radius, which is 7, right? Okay, now I'm just trying to make sure I didn't mess up something. Okay. What's the relationship between x and y now? Do you see it's Pythagorean? Except this length of the right triangle is not x, it's x over 2. All right, so I'm going to write y squared plus, what does Pythagoras say about these three sides? X over 2 squared equals 49. 7 squared is 49. Okay. All right, I'm trying to get x alone. So how do you get x alone? I want to get x in terms of y so I can integrate with respect to y once y is here. So how to get x alone? First, subtract. So x squared, how about, I'll just write x squared over 4 here, right? Equals 49 minus y squared. Then what? Multiply by 4. Okay, x squared is 4 times 49 minus y squared. Or you can distribute it if you want. And so x is just the square root of that. Leave the 2 outside. All right, so let's use that. That's x in terms of y. Before we use similar triangles, this time we use Pythagoras, right? So delta A in terms of just y, which is better because I don't know how to integrate x with respect to y. I can't do that. Is x, which is 2 rad 49 minus y squared delta y. This is all in terms of y. So can I integrate now? A equals what integral? Remember, this step is saying, let's take every single rectangle I could draw, infinitesimally thin. As delta y goes to dy, infinitesimally thin, almost zero. I have infinitely many rectangles I want to add up. So how do you write that? 2 times the integral from, what's the y's doing? 0 to 7, right? So 0 to 7 of rad 49 minus y squared dy. All right, do you know how to integrate that? Yes, you do. Does that sound familiar at all from last week? It's not a U sub. It's a trig sub. All right, so let's change gears for a second and do some trig sub stuff separately, like the little scratch paper over here. Let's say I'm just interested in this. Right, just that part. The rest is just numbers. Don't worry about that. How do you construct the right triangle such that this is one of the sides? I want to construct the right triangle such that 49 minus y squared is in one of these sides. So any ideas? What sides am I placing? Y and 7, right? Okay. Where's the 7? Where's the y? So this is one of the sides. Could I put y here and 7 here? No, because that gives you y squared plus 7 squared. So 7's got to be hypotenuse? All right. What if, just for the sake of argument, what if I made y the hypotenuse? What's bad about that? Let's say this is a. How do you get a? A squared plus 7 squared equals y squared. So a squared is y squared minus 49. That's a sign issue. I wanted 49 minus y squared. So you're correct. Put the 7 here. Put the y there. Okay. So I don't like that. So go away. No, not you. Go away, go away, go away. So you got to play around where you put the y. That's all. So I'll put the y here and the 7 here. Now does it work? A squared plus y squared is 49. So a squared is 49 minus y squared. Yeah, this is working out. So this is the side. Square root of 49 minus y squared. Now, what's the relationship between theta, y, and 7? Remember, this is trig sub. I want to put in tangents or sines or cosines or something in here. The sine of theta is what over what? So katoa, y over 7. So what's y alone? Just y alone. How do you get rid of the 7? Multiply by 7. All right, so I'm just going to say y equals that. Now the whole point of this is I need a dy. I need a y. I got to replace them for y, but I need to replace them for dy too. So what's dy? Start you off. 7 cosine theta d theta. Right. So wherever I see dy, I'm going to write that right there. Wherever I see y, I'm going to write that right there. Okay. Integral of the square root of 49 minus y squared. Well, if you square y, you get 49 sine squared. Okay. Close the radical, times dy is 7 cosine theta d theta. Okay. So remember, the game here is to simplify it in such a way that you can integrate with respect to theta. And then go back to y. Using probably an arc sign as a sign in here. But you see enough. All right. So, what about the 49s? They're factors. Factor them out. What's the square root of 49? 7. Factor out the 7. Take out the 7. I got 49 times the square root times the integral of the square root of what? What's left? Let's clean this up a little bit. I pulled out rad 49, which is 7, times this other 7, gives you 49, times the integral of the square root of what's left. If you took out 49, what's left? 1 minus sine squared. What's 1 minus sine squared? Cosine squared. What's the square root of cosine squared? Cosine times cosine is cosine squared. Aha. You know how to integrate cosine squared. You could do by parts, or you can use a trig identity. What's the trig identity we know for cosine squared? No. No, we have a trig identity that makes cosine squared easy to integrate because there's no square. Remember the double angle formula we talked about? You forgot? Cosine squared is 1 plus cosine 2 theta, right, over 2. I'm going to bring out the 1/2 with the 49 halves. How about that? Okay, so now we're integrating this. Well, that's nice because this is a U sub. That's not so bad. Trig sub, U sub, a little everything. All right, so if U is, what's U if we're doing this piece? 2 theta. So who's du? 2 d theta, right? So I'm going to replace d theta with du over 2. Okay, so what's the antiderivative of cosine u du over 2? What's the antiderivative of the cosine of u du? What's the antiderivative of the cosine of u du? Now the derivative of the cosine is negative sign, so the antiderivative of the cosine is just sine, right? So the antiderivative of the cosine of u du over 2 is sine of u over 2, yeah? What, this part here? This here? Here. There? Well, I didn't, what? Oh, well, there's a trig identity that we talked about. That whenever you see cosine squared theta, to integrate it, it's a lot easier to integrate 1 plus cosine 2 theta over 2. That's a trig identity. It's true for all theta. Okay? It's just a lot easier. And if it says sine squared here, you put a minus. That's it. That's the only difference. The rest is the same. It just makes life easier. Unless you want to do by parts. You can do by parts here. But that's a cyclic by parts. Oh, it's a mess. So anyhow, so the antiderivative of cosine u du over 2, because it's over 2, right, is sine of u over 2. So I get, let me put this in the next page, equals 49 halves of, oh, by the way, we didn't say it, but the antiderivative of 1 d theta is just antiderivative of 1 d theta, just theta, right? Okay, so we got 49 halves times theta plus the sine of u over 2 plus c. Okay. How do you get back to y? Because remember, we started with y, right? Can you get rid of the thetas to get back to y? If I'm integrating a function with respect to y, hopefully I could get back to y, because I have limits of integration in terms of y, right? Yeah. So, how do you get theta to look like a y? Yeah, go back to the triangle, and remember what we originally wrote. The sine of theta is y over 7. So what's theta? How do you get rid of sine? I just want theta. What's the opposite of sine? How do you cancel sine? Do arc sine to both sides. So theta is arc sine of y over 7. Okay. So we get 49 halves times the arc sine of y over 7 plus stuff. Well, do you remember this on the first test? The sine of the sum of two angles is the sine of the first times the cosine of the second plus the sine of the, cosine of the first times the sine of the second. You remember that? We used that on the first test. I gave it to you. Why do I bring that up? Well, because if you know that, you know the sine of 2 theta. What if I put in theta in both of these? Same thing in both of these. What's the sine of 2 thetas? Isn't that 2 theta? Theta plus theta is 2 theta? That's going to be the sine of theta times the cosine of theta plus the cosine of theta times the sine of theta. Isn't this the same thing? Sine times cosine, cosine times sine, same thing, right? Commutativity of multiplication, yes? So could I write that as 2 times sine theta, cosine theta if I wanted to? So what's 1/2 of sine of 2 theta? It's half of this. What's half of this? Sine times cosine. So plus sine times cosine. Wait a minute. What's the sine of this angle? Y over 7. What's the cosine of this angle? How do you get cosine? Sine is opposite of hypotenuse. Cosine? Adjacent over hypotenuse, right? Sine times cosine. That's the antiderivative. Oy. Okay, let's use it. Remember what we were doing? We're doing the definite integral from 0 to 7 times 2. But the indefinite integral is this ginormous mess. We've got to multiply that by 2, so what happens with the 2's? Goes away. Evaluate it from 0 to 7, so what happens with the plus c? Goes away. So this is what you end up doing. Whoops. What we were trying to figure out, 2 times the integral from 0 to 7 of rad 49 minus y squared dy. Stop doing that. Why does it do that? Is equal to 49 times, or the 2's going away, this mess, right? I think I have this somewhere. All right. Arc sine of y over 7 plus plus y over 7 times rad 49 minus y squared over 7. And this whole mess is being evaluated from 0 to 7. Okay. So, what's 49 times, let's plug in 7. The arc sine of 7 over 7, remember this is a y. It looks weird, but it's y. I'm plugging in 7. What's the arc sine of 7 over 7? What's the arc sine of 1? What's the angle whose sine is 1? Nobody knows? The angle whose sine is 1. Put it in your calculator. Do second sine of 1. Second sine is arc sine, right? You get 1.571. That's pi over 2. All right, so this is pi over 2. What if I plug in 7 here? 7 over 7 is usually, last time I checked, it's 1. Okay. What's 49 minus 7 squared? 0. Rad 0, 0, 0 over 7 is 0. 0 times anything is 0. So it's pi over 2 plus 0. That's what happens when you plug in 7. Minus what happens when you plug in 0. What's the arc sine of 0 sevenths? Well, 0 sevenths is 0. What's the angle whose sine is 0? Do it on a calculator if you have to. Second sine of 0 is 0. Plug in 0 over here. 0 sevenths. 0 times anything? 0. So there's a bunch of zeros here, and you get 49 pi over 2 cubic inches, if we start off with inches. But we said that. We knew that. Dun, 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 check. We know this works. This process works. Look, didn't we say at the very beginning, if this is a semicircle, whose diameter is 14, the radius is 7, pi r squared therefore is pi times 7 squared is 49 pi. But that's the whole circle. I want a semicircle. So 49 pi over 2. After all this freaking mess, that's what you got. Good. The point isn't, I know how to do this a different way. The point is, do you know how to do it this way, new way? So when you don't know how to do it, you can do it anyway. Now this really got really hairy with trig sub. But hey, you know trig sub, you know u sub, you know by parts, it's going to pop up. Stuff pops up when you least expect it. You got to know it. All righty. Okay, you know what? Why don't we break here? Take a little 5-minute break. Okay, so it's 8:08 according to this. So roughly, what, 8:13-ish? Okay, we'll be back. 5 minutes, dead air. Fast forward, okay? All right, we're back for more fun and games. Some of us are still missing. That's why I don't like giving breaks, but such is life. Here we go. So, remember what we just did. We found the area of this semicircle, right? What other way? If I gave you this thing, how else would you do it? Well, you could argue that this is the area of a semicircle, and from 0 to 7, it's a quarter of a semicircle, and yeah, you can play with this. Yeah, you can get around that. But I was trying to show you an example where trig sub pops up. Yeah, in this case, you could say, no, that I already know. It's silly. I already know the area of a circle, so yeah. It's sort of, this is sort of like circular reasoning, but no pun intended. But, what? Well, where's the trig sub come from without the triangle?
Well, I mean, like, I just like know the format of it.
Oh, well, as long as all this other stuff works out correctly, that's fine. If you're able to come up with this on your own? Yeah, that's fine. Okay, now, this is what I want to do. I didn't really want the area of a circle. That's silly, I know that already. What if I took this thing and revolved it around the y-axis, or around this axis of symmetry here, and I get a hemisphere, don't I? How do you get the volume of the hemisphere? Again, you probably know the volume formula for a sphere, do you? Good, so you're screwed. So let's do it this way. See, I knew it. I'm not going to tell you what it is. All right, so let's find out. Yeah, that's what it is. Okay, good. So let's find out what it is. Well, so let's revisit this whole situation here, but now I'm doing it in 3D. Okay, so it's like a hemisphere. No, that's not it. It's like a hemisphere. I mean, a semicircle, but it's not. It's a hemisphere. All right, so it has some depth to it. All right, let's do the same thing we did with the cone. Take a slice up here. I can't draw right. I'll pretend that's a disc, okay? Yeah, don't laugh. Yeah, you try to do this. All right, pretend that's a disc, like a dime, like last time. Remember that? So we're going to say, again, this is a delta y thickness. We're going to let that go to 0. And again, the volume of a cylinder. How do you get the volume of a cylinder? It's the area of the face, which in this case is a circle, times the height, which in this case, okay, so what's your Riemann statement for the volume of that one slice, that one cylinder? Huh? Say, I didn't hear you. Times, well, it's not x though. That gives you an area. That's what we did for area, x times delta y. It's delta y, the height of the cylinder, times the area of the face. The face is a circle. How did it get the area of a circle? Pi r squared, right? Whoops. Right, but what's r in this case? Remember, we called this the whole rectangle last time had a length of x. And this bottom part here had a length of 14 inches, right? The same situation. The cross-section is still that semicircle thing. So what's the radius? It's x what? No, of this thing. Depending on how high you are, x is going to get shorter and shorter, right? Up here, x is really short. Over here, x. Down here, x is 7. Up here, x is 0, basically, right? But what's the radius? Down here, x is 14. Up here, x is, I don't know what the hell it is. X here is 0. But here, it's what? X over 2. And don't forget, it's pi r squared that I want. Okay. So the Riemann statement for the volume of this hemisphere, okay, is delta V is pi r squared delta y. But again, I can't think ahead. What are you going to do? You're going to add up all of these cylindrical volumes, infinitely many of them, as delta y goes to 0, becomes dy, infinitesimally thin. And again, I have infinitely many cylinders to add up their volumes, right? So what does that mean? You're going to integrate something with respect to y. I can't have an x here. Okay, but before, didn't we have an expression relating x and y? Didn't we have x squared over, before we wanted x, right? We needed x. But look what x squared over 4 is. It's 49 minus y squared, right? Why do I care about x squared over 4? Because what is this? This is x squared over 4. So delta v is pi times 49 minus y squared delta y. Notice how easy this is. There's no trig sub here. This is just power rule. There's no even u sub here if you integrate this with respect to y. It's a lot easier. The volume is actually easier than the area. That's weird, but there you go. So let's translate this Riemann statement to an integral. How would you write this as an integral to get the volume of the hemisphere? I'll start you off. Pi times the integral from 0 to 7 of 49 minus y squared, what? dy. Right? In the limit, delta y goes to dy, infinitesimally small, basically 0. All right, so isn't this just power rule? Is that too sloppy? Hang on. Minus y squared quantity dy. Okay? All right, so how do you integrate that? What's the antiderivative? 49 dy. 49y. What's the antiderivative of y squared dy? Y cubed over 3. There's no u sub, there's no trig sub, there's nothing special here. It's just power rule. So v equals pi times 49y minus y cubed over 3, quantity evaluated from 0 to 7 as per the fundamental theorem of calculus part 1, which says, let's do it down here, which says you plug in 7, so you got 49 times 7. Isn't that 7 cubed, by the way? 49 times 7 is 7 squared times 7. Minus 7 cubed over 3. Minus plug in 0. 49 times 0 and 0 cubed, and all of this times pi. What did you get? What's 7 cubed minus 7 cubed over 3? All right, let me ask you a different way. What's a whole pie minus a third of the pie? Somebody ate my apple pie. 2/3 of the pie, but the pie is 7/3. Okay, so it's 2/3 of 7 cubed times pi. Now that shouldn't be surprising. Because the volume of a sphere is, does anyone remember it now? Not 2/3. 4/3 pi r cubed. R is 7. There's the thirds, there's the pi. Why is it not 4? 4/3 pi r cubed is the volume of a sphere. But this is a hemisphere, so half of 4 is 2. Good. All right, and that works out, by the way, if you want to work it out. It's 686 pi cubic inches, which is approximately 718.378 cubic inches if you plug this into Ziggy, or if you plug this into Ziggy. All righty? So that's your basic introduction of how to use integrals to get areas and volumes and stuff like that. Okay. So, let's play around some more with that. Consider the following area. No, actually volume. Are you ready? Any questions up to here? The volume thing was easy. No tricks, no nothing, right? The area was insane. Holy cow, what a mess. So if you don't remember the area of a circle, you're really in trouble. Okay. So let's try this. What if I take a look at this volume? It's made up of y equals e to the negative x. Remember e to the negative x from the test? It's not a good drawing. It should go asymptotically to the x-axis. Yeah, I don't like it. This is all crooked. What is going on? All right, you know what? Let's be real precise. Are you ready? Let's do this. Let's do this. That. There. How do you like that? And here's y to the negative x. Something like this, okay? And so it doesn't start dipping up. It goes back down to x-axis, okay? So y equals e to the negative x, okay? And this is on the test, I think, number 4. And we found the area under the curve from 0 to infinity. It was from 0 to ln of 2 was 1/2. From ln of 2 to infinity was 1/2. The whole area was 1, right? Okay. That's not my question. My question is, what's the volume from 0 to 1? So I'm just going up to here, okay? If you revolve this thing around the x-axis. Okay, so what's my Riemann statement? Now I'm taking just the area from 0 to 1, and I'm revolving that around the y-axis. So what's your delta V now? What's your Riemann statement for the volume of this cylinder here? I can't draw it. Yeah, something like that. So notice I'm slicing this into rectangles. I'm revolving the rectangles around the x-axis. I get that cylinder thing again. What's the thickness? Delta x. What's the radius? How big is that radius? It's bigger at x equals 0. It's smaller at x equals 1. But at x, any x in between, what would you call this? What's the radius? It's the height of the rectangle. It's the function itself. It's e to the negative x, right? Whoops. So, the area of the face is pi r squared. The thickness is delta x. What should I write? What's the area of the face? Area of the circle. What is it? I see it on your mouth. Say it. I heard it. No, I didn't hear it yet. How do you get the area of the circle? Pi r squared. But what's r? What's e to the negative x squared is e to the negative 2x. What's the thickness? That's the area of the face times the thickness gives me the volume of this whole cylinder. Delta x. Good. There's your Riemann statement. Okay. Notice what's nice about this is all in terms of x already. I don't have to play any gymnastics to get y in terms of x or x in terms of y or anything like that. It's done. So I'm ready to integrate. V is what integral? Pi times the integral from 0 to 1, because I'm doing this in terms of delta x, right? So it's x's. Of e to the negative 2x dx. Okay, good. Some people might call this the disk method, but it's the same thing we just did, nothing different. These little disks. I'm adding up all the volumes of all these disks, okay? Alrighty, and so how do you anti-differentiate that? How do you anti-differentiate this? What method do you use? Trig sub what? U sub. U is negative 2x. Du is negative 2 dx. So we replace dx with negative 1/2 du. So I get negative pi over 2 e to the u du. How do you integrate e to the u du? Get e to the u, but u is? Okay, so it's negative pi over 2 e to the u plus c, but evaluating from 0 to 1. So I get negative pi over 2 times e to the negative 2 minus e to the 0. There you go. Okay, that's an answer, but e to the 0, you know it's 1. How about we write that? And you can leave it like that, but realize that e to the negative 2 is very small. So e to the negative 2 minus 1 is really negative. When you multiply negative times a negative, you get positive. This is fine, but I would write it this way. I'm going to say pi over 2 times 1 minus 1 over e squared. That's what it is. And if x is in inches, that's in cubic inches. Let's say. They didn't give you x units, so you don't have to say units in this question. If you punch that into a calculator, it's about 1.36 something. It's always nice to have a decimal equivalent to check. Okay? Why don't we check this with Ziggy? What the heck? I'm going to punch this into Ziggy. I'm going to punch this into Ziggy. We better get the same decimals, right? That's a check. Okay, so pi times the integral from 0 to 1. Whoops, wrong thing. Go away. Okay. Where did Ziggy go? There he is. Okay, so turning it on. Okay, how do I do an integral on Ziggy now? Math 9. Okay, so go to math. Go to 9. And what you type is the integrand. This mess, right? So it's e to the, that's second ln, because it's yellow, right? The e to the x is yellow, of negative 2x, right? So it's negative 2x, close that. Then what do you write? Comma, what? X, then what? Comma 0, comma 1. And that's not the answer. Why? What's missing? There's a pi. Okay, so if I want pi in there, I could just multiply by pi, or I could do the whole thing over again. Second enter, then move over here and throw in, let's say, a second insert, second pi. And now I get my decimal answer is approximately 1.358. I said 36. Okay. Is that the same thing as what we got? Well, let's see as a decimal if that matches. Okay, so it's quantity, pi, over 2, times the quantity, 1 minus 1 over, or I could just write e to the negative 2, but over second e squared. Close the e, close the product. And do we get 1.3582-ish? We do. So that's just a little check, okay? The decimal equivalent of the answer, the decimal equivalent of the question, match. That's as good a check as you're going to get on the Ziggy. Remember, Hal can do better, but no right clicks. Go away. All right, any questions about that one, that area? I mean, that volume. Actually, that wasn't really the question I had in mind. Take a look at this. Where am I? What if I don't go from 0 to 1? What if I go to from 0 to infinity? So the setup is the same. The Riemann statement is the same, but my limits of integration are from 0 to infinity. Let's work that out a little bit. What's the integral? What was it? Pi times the integral from 0 to infinity of e to the negative 2x dx. What's bad about this? What's different? By the way, this is a famous question. This is called a Gabriel's horn question. Can you imagine if you take this volume, if you take this thing, rotate it around the x-axis, and go forever? Remember, the e to the negative x never actually touches the x-axis, right? It's asymptotic to the x-axis. If you go on forever and you pretend that's the shape of a horn, that's Archangel Gabriel's horn. He's got this big-ass horn to call all the angels when he's in trouble. You ever hear of this? Gabriel's horn? Never heard of archangels? They got big-ass horns? No? You never knew about this? Well, this is how big Gabriel's horn is. My question is, what's the volume of this horn? Can he blow it? What if the volume is undefined? It's infinite. You can't blow that, can you? Even an archangel can't do it. So does this exist? All right. Did I give it away? What's bad about this? You have to rewrite it as a limit because it's an improper integral. Okay. The limit as b goes to infinity, the integral from 0 to b of e to the negative 2x dx. Now remember, we did this already. U was negative 2x, du is negative 2 dx. Replace dx with negative 1/2 du. So you're integrating negative 1/2 e to the u du. What's the integral of e to the u du? E to the u, and u is negative 2x. Okay, so what do I get? Don't forget the pi. It's in here somewhere. So you get pi negative 1/2 e to the u, e to the negative 2x. Isn't that really this? Negative 1/2 e to the negative 2x is this. E to the negative 2x in the numerator is e to the positive 2x in the denominator. And I need to take the limit as b gets crazy for this integral from 0 to b. All right, so what do you do next? Plug in. Who? B. Right, okay, so it's pi times the limit as b goes to infinity of negative 1 over 2 e to the 2b minus a negative is plus 1 over 2 times e to the 0, but e to the 0 is 1. Okay. Didn't we get a limit like this on the test? What is this limit? Sort of like we did once something like this. That limit is 1/2. So you get pi times 1/2 is pi over 2 cubic units. So if x is in feet, the volume that Archangel Gabriel has to blow out of the horn is just pi over 2 cubic feet. That's not too bad. 1.5 cubic feet? We can do that. It's an Archangel. You can do anything. This, in other words, this limit exists. This is a very famous limit. This comes up. Okay? That's an Archangel Gabriel question. Look it up on the internet. I bet you there's a Wikipedia chapter on this stuff. Any improper integral where you have some kind of a weird fraction that's bottom heavy, those are all Archangel Gabriel questions. The volume of his horn. So the volume of the horn, even though it's infinitely long, the volume of the horn is finite. It's only about 1.5 something. Almost 1.6. That's not a lot. How is that possible? That's not intuitively obvious, is it? If the thing is infinitely long, it has a finite volume? What? Or put it this way. To build it, you can't build it. How much brass do you freaking need? What if it's like a... Pretend it's not a horn. Pretend it's a can for a potted plant, or a can of paint. How much paint does it hold? Say you take that horn and you stick it up vertically. It goes infinitely high. But you fill it with paint. What was the volume? 1.5-ish, 1.571, right? The volume of paint in that humongously huge horn is just 1.5 cubic feet, let's say. But it's infinitely long. So how the hell do you build this can? You can't. How much brass do you need? You don't got enough. Right? This doesn't make no sense. That's improper integrals. All righty. Question. Okay. Let's say, all right, let me give you this situation. Is this a good one? Let's see, what's a good one? How about this? Okay, I'm going to go. Okay, let's say I give you this situation. Any questions up to here? We good? Okay. Okay. Let's say I give you these two curves. Let's play this game again. I like that. All right, so you have this curve y equals x squared. No. Say it looks like that, right? That's y equals x squared. And here's the origin. And let's say this is 8, and I have y equals 8 minus x squared. Something like this. Y equals 8 minus x squared. Consider that area bounded by the two curves. Okay? Yeah. Consider that area bounded by the two curves. You could find that area, couldn't you? Let me ask that. What is that area? What if I break this up into rectangles? and I add up all the rectangles. Rectangle touches this curve, rectangle touches this curve, it's vertical. I know it doesn't look it, but it is, okay? What's the thickness of the rectangle? Delta x. What's the height? How long is it from here to here? For any x value between this point of intersection and that point of intersection. Say for any x, let's say this is x, right? What's this height from here to here? I need base times height, right? Not necessarily. Isn't it this y value minus this y value? Isn't this y value 8 minus x squared? Isn't this y value x squared? So what's your delta A? What's your Riemann statement for the area of that rectangle? It's higher y value minus lower y value. That's the height. Times the thickness is what? What's your thickness? Delta x. They always say it's a delta x. It's horizontal thickness. Okay, and what is 8 minus x squared minus x squared? It's really just 8 minus 2x squared. Okay. Notice this is all in terms of x, so I don't have to do any weird stuff to get rid of x and y and all that stuff. So what's the area? How to get all the area of every single rectangle I could have drawn. The infinitely thin rectangle. It's the integral from, we don't know from what to what. Do we know the x value of this point of intersection? Do we know the x value of this point of intersection? How do you find out where these two curves intersect? Set them equal to each other. How do you solve for x? Add x squared, okay. And divide by 2. And you get x is plus or minus 2, right? So you get here and you get here. X is negative 2, here x is positive 2. So, negative 2 to 2, 8 minus 2x squared dx. All right, so integrate. A equals what? 8 dx gives you 8x. Negative 2x squared dx gives you negative 2x cubed over 3. Evaluate that from negative 2 to 2. By the way, by symmetry, you probably could have simplified this a little bit and just done from 0 to 2 and double your answer. It would be easier, but whatever. The arithmetic anyway. So, all right, let me get rid of this stuff. Make some room. And so A equals, let's plug in 2. You get 16 minus 2 cubed is 8 times 2 is 16, so minus 16 thirds. Minus plug in negative 2, I get 2 times negative 2 is negative 16. Negative 2 cubed is negative 8, times a negative 2 is a positive 16. And so you do both of these. Well, what's 16 minus a third of 16? Didn't we play this game a minute ago? I have an apple pie and someone ate a third of the apple pie. What's left of the apple pie for me to eat? 2/3 of it. Same thing here. So I get 2/3 of 16 minus, but wait, what's 16 thirds minus 16 instead of 16 minus 16 thirds? What's the only difference when you change the order of subtraction? What's the only difference? This is 16 minus 16 thirds. This is 16 thirds minus 16. All I changed was the sign. So I get minus a negative 2/3 of 16. How do you subtract the negative? You add a positive. What's 2/3 plus 2/3 of stuff? What's 2/3 of stuff plus 2/3 of stuff? 4/3 of stuff. What's 4 times 16? 64 thirds square inches or something, whatever the units are. Okay, that's an area question. That's not what I had in mind. Oh, that's a good question. What I had in mind was the same idea, the same setup, but that's the base of some kind of a weird sculpture, okay? Or a block of cheese, let's say. That's the base of it. But if you take a look at that block of cheese, it's coming out of that's the ground, right? This picture, that's the ground. It's coming out of the ground in such a way as if you take slices of cheese perpendicular to the x-axis, you get squares. What's the volume of the block of cheese? All right, here we go. So let me do this a little more like in perspective. Here's the y-axis. Here's the x-axis. Here's y equals x squared. Here's negative 8 minus x squared. But now the base, these rectangles that we drew before, wait, go away. That rectangle, that's the base. I can't draw a perpendicular. That base of a square that comes out of the picture. Okay? This rectangle is parallel to the y-axis. This is the x-axis. This is coming out of the page, like a z-axis. Can you give me a Riemann statement for the volume of that square slice? Like American cheese is little square slices, right? What's the volume of that slice? How do you get, remember, when it was a circle, when it was a cylinder, I said the area of the face, pi r squared times the thickness. But the face isn't a circle anymore. It's a square. But that's easier. What's the area of a square? Side times side. Side squared. That's why they call it a square. Why do they call it a cube? Because you cube the side to get the volume. Okay. So what's your delta A? What's, not delta A, delta V, the volume of that slice of cheese? It's the side squared times the thickness. What's the thickness now? It's still delta X. What's the side? The side is still this y value minus that y value, right? It was 8 minus x squared minus x squared. So it's 8 minus x squared is the side of the square. Square it is the area of the square times delta x is the volume of that square slice. It doesn't have to be a circle all the time. Notice there's no pi. So what's the whole volume? If you add up all these square slices, they're infinitesimally thin, all of them from this point of intersection to this point of intersection. Realize that the slices are all different sizes. Here, it's really humongous, if you do it right on the y-axis, right? Here, it's really small. Right on this point of intersection, it's 0. So all these slices have different volumes. So some are huge, some are small. How do you add them all up? You take the... Oh, it is 2x, I'm sorry. Thank you. It is 2x, right? It was 8 minus x squared minus x squared. Okay, so what's the volume? The what? Integral from? Remember, we know the intersections. Negative 2 to 2 of this thing. All right, so if it was just this wasn't here, this would just be power rule, right? But with this here, how would you do it? Is it a U sub? If you do U is what then? 8 minus 2x squared? Then what's du? Negative 4x dx, right? Yeah, all I have is a dx. I don't have an x dx. Can't do it. Can't do it. If there was an x dx, yeah. Or if it was just dx here, no x dx, just x, yeah. I can't do a u sub here. Doesn't work. Sorry. But actually, there's an easy way to go with this. What's another way? Foil it out. Okay. So let's foil it out. So v equals, let's foil this out. First times first, outer times outer, inner times inner, right? So we get 16. Then outer times outer is minus 16x squared plus another minus 16x squared, so minus 32x squared. And then last times last is positive 4x to the fourth. And if you want to do foil the old-fashioned way, be my guest. Okay, now we didn't integrate yet. So do so. What's the antiderivative? 16x minus what? 32x cubed over 3 plus 4x to the fifth over 5 evaluated from negative 2 to 2. So V becomes, holy Moses, you're going to plug in 2 into this? 2 times 16 is 32. 2 cubed is 8 times 32 is 64, 128, 256 thirds. Then 2 to the 5th is 32 times 4 is, what the frick is it? 32 times 4 is 128? Fifths. That's if we plug in positive 2. Minus. Am I good? Did I mess up? This guy? 8 times 8 is usually 64. Yeah, right. Cool. Just seeing if you're awake. See, it's late. It's almost 9 o'clock. I got to do these things. Oh, yeah, you're right. 64. Yeah, so everybody's perfect. I know. Except for me. Is that all that was bad? So 2 times 64 is 128. Okay. So we're good with now? It's good? Okay. See, who said I can do arithmetic? Okay. Now plug in negative 2. Well, if you plug in negative 2, you get negative 128. If you plug in negative 2, now this is a negative 8 times a negative 32, you get positive 256 thirds. If you plug in a negative 2, this becomes a negative 32 times the 4 is negative 128 fifths. Equals, holy Moses. Well, what's 128 minus a negative 128? You add them, so it's 256. What's negative 256 thirds minus a positive 256 thirds? Do you get 0 or do you get double? You get double. Double positive or negative? Negative 512 thirds. Is that a multiple of 3? It's not. Damn. Wait. 512 thirds. And it's 128 minus a negative 128 fifths. When you subtract the negative, you're really adding, so you end up with plus 256 fifths. And you can play with this and get an easier answer. That's it. I'm done. I'm getting tired of this question. It's driving me crazy. Yeah, you can get common denominators, or you throw it in the calculator, get a decimal, whatever you want to do. Okay, there's your answer. All right, that's called volume of a known cross section. When the slice is not necessarily a circle, it could be a square, it could be a triangle, it could be something else. You can still set up a Riemann sum. You can still set up a Riemann statement and get a Riemann sum. So, all kinds of weird shapes now. Areas and volumes, all kinds of weird shapes. All right, we have one last thing to discuss. We did area, we did volume. One more thing. Arc length. How do you measure the length of a curve? I know how to measure the length of a line, right? What's the shortest distance between 2 points? The straight line segment joining those 2 points. What's the length of it? Distance formula. Or, if this is C, delta x is A, delta y is B, it's just Pythagoras. Distance formula is just Pythagoras. That's if it's a straight line segment. What if you got a curvy path that you need to know the length of it? How do you do that? You have to talk about arc length, okay? So let's talk about that. That's just one last little topic in this unit. We got to get a feel for it. All right, so let's say you have some wacky function, right? And I want to know the length from here to here. And it's not a distance formula because that's a straight line segment. It's not it. In fact, we're going to do the straight line segment from here to here. Is it shorter or longer than that curve? It's actually shorter, right? So that's an underestimate, I guess, but it's a bad underestimate. All right, so what are you going to do? Well, what you do is you do like a Riemann statement. You blow up a little piece of it, all right? Let's blow it up. Area of detail. Okay? Pretend that little piece, now pretend it's really small. Like you need a microscope to see it, okay? Pretend that length of that arc is almost straight. I'm going to blow it up. Almost straight. Pretend it is straight. There's a delta x, there's a delta y, and there's a delta, I'm going to call it L for arc length. Usually called delta z, I guess, whatever. Okay? I can get an equation for delta L, can't I? Because this is Cartesian. What? What does that mean? Descartes, you ever hear of René Descartes? He made up graph paper where everywhere you can get a vertical and you can get a horizontal, right? So I can always measure a horizontal distance in delta x and a vertical distance in delta y. That's what it means to be Cartesian. Or rectilinear. Ever hear of rectilinear? Oh, polar. No, we're not doing polar. We might touch on polar, but it's not really part of this course. You could extend this to polar very easily, but let's not go there yet. All right, so let's talk about that. Well, what does Pythagoras say about that? He says that delta x squared plus, what does Pythagoras say about this right triangle? Delta y squared equals delta L squared. Well, let's cut to the chase. Let's take the limit as delta x goes to 0. Let's make this infinitesimally small, this infinitesimally small, and this infinitesimally small, and you get dx squared plus dy squared equals dl squared. Okay. Now, let's do a little gymnastics. Are you ready? There's a lot of ways you could do this, but what if I divided everything by delta dx squared? Now remember, dx is not 0, it's damn close to 0. I can divide by dx. Okay, what's dx squared divided by itself? 1. What's dy dx? The derivative. I'm going to write it this way. F prime of x squared. Right? And that's going to be dl dx squared. I could have written this dy dx squared. I'm going to write it. Same thing as f prime, right? In this context, dy dx squared. Now remember what I'm trying to do. I'm trying to get L. I'm trying to get a formula for L, basically. How do you get L alone? Well, first of all, how do you get rid of this? That's square root. So dl dx is going to be the square root of 1 plus dy dx squared. How do I get rid of this? Multiply by it. So dl equals the square root of 1 plus dy dx squared times dx. Now that's dl. How do you get rid of d so I get L? And they differentiate both sides. So this is sort of like solving a differential equation. So L is, in fact, the integral of that with respect to x from a to b, let's say. Whatever x value you start at, whatever x value you stop at. So there's your formula for arc length. Okay, so if x is like, 2 and x is 5, you do the integral from 2 to 5 of this mess. Okay. So let's see if we can try a question like that. Let's say I want the arc length of something easy. How about this curve? Y equals x cubed. Goes through 0, 0. Let's say I want the length of this curve from x equals 0 to x equals 5. I want this length right here. Now remember the formula. The length is the integral from a to b of the square root of 1 plus the derivative squared, derivative with respect to x, dx, right? All right, y is x cubed. What's dy dx? That's y. What's dy dx? 3x squared. But I don't want dy dx. I want dy dx squared. So what's dy dx squared? I didn't hear it. What? 9x to the 4th. Okay. Fine. And so let's do it. The arc length is the integral from 0 to 5 of the square root of 1 plus 9x to the 4th dx. Okay. So how do you integrate that? No, not a u sub. Because if u is 1 plus 9x to the 4th, you don't get just dx, right? So trig sub, no, because trig sub with a plus is arctan without a rad. So trig sub doesn't work here either. There is no closed form antiderivative for this problem. You can't do this analytically. You can only give me a numerical estimate. How do you do that? Math 9. Okay, so let's drag out math 9. Okay, so, whoops, I gotta turn this off here. Okay. Okay, so let's do a math 9 on this mess and get an estimate for the answer. So you do math 9 of the square root of 1 plus 9x to the 4th. Close the radical. Then what? Comma x. Then what? Comma 0. Comma 5. That's it. Just let Ziggy do the work. If there's no way to do this exactly, this is all I want you to do. This is all you can do. And you get an estimate that's about 125.680. Yeah, that's about right. Okay, so L, the arc length, is about 125, about, remember, equals with a dot, means I'm rounding off, 0.680. And if they don't give you units, don't give units, right? But the idea is if, where's my mouse? Okay, if x is measured in like feet, right? If x is in feet, the length is in, if x is in feet, the area, square feet. If the length, if x is in feet, the volume, cubic feet. But if x is in feet, the arc length is still feet, okay? But I didn't say feet, so don't worry about it. But if they give you units here, like this is inches, you better say inches here, right? All right, let's revisit the question a moment ago. Remember the Gabriel's horn thing? What's the arc length? What is the length of the horn? We said it was infinite. Is it really? Let's see. Let's find out. Remember the setup. It's y equals e to the negative x. And originally we did the area. We did the area on the test, and we did the volume for Gabriel's horn from 0 to infinity, right? Well, I want the arc length from 0 to infinity. For x goes from 0 to infinity, what is this arc length? From here to forever. Because this doesn't hit the x-axis, right? So it keeps on going. Until you hit the x-axis, you don't. Okay, so remember the formula. What is it now? L equals the integral from, what's the formula we came up with? A to b of the square root of 1 plus dy dx squared, and then dx is outside the radical? Okay. So if y is e to the negative x, what's dy dx? Negative e to the negative x. And what's dy dx squared? Because that's what I want. E to the negative 2x, right? Because then that negative goes away. This is technically negative 1 over e to the x. This is technically 1 over e to the 2x. Okay, so let's do this little formula thingy. L equals the integral from, what are the x values going? From 0 to what? Infinity. Of the square root of 1 plus, I guess I'll write it this way. Can you anti-differentiate that? Oh, yeah, that's right. Yeah, I don't know. I don't think so. I mean, think about it. What if the inside? See, what would be nice is if the inside was a perfect square, then you could square root it, right? I don't think it is though, because if you want, this is going to be e to the 2x plus 1 over e to the 2x. Does that help? I'm thinking 1, getting common denominators is e to the 2x over e to the 2x. So when you add them, you get a common denominator of e to the 2x. Sometimes that might help. Nah, didn't help. Even if you square root this and get e to the negative x outside, that's not a du. If that's a u, I can't do this analytically. So what are you going to do? Math 9, but wait, don't forget that this is what kind of integral? It's improper. So I can't just do math 9 because math 9 says put in, f int, right? F n int, and then you put y1 comma x comma 0 comma what? I can't put infinity. So I got to do some kind of like a convergence table. Hopefully it converges. I don't know. Maybe this will be a divergence table. Didn't we say this is probably infinitely long? All right, I want to evaluate the limit. Now you tell me, what kind? A, B, or C? B, right? As B goes to infinity of the integral from 0 to B of the square root of 1 plus 1 over e to the 2x dx, wasn't it? That's what it was, right? Yes, it was. Okay. So what you do is you make a little table for bigger and bigger values of b, bigger than 0. So let's say 1, 10, 100. Didn't we have a question like this in the test? I built the table for you. And I'm evaluating from 0 to b, whatever b is, but it's getting big and big and big, of this mess. Now that you can do in fint. Aha. So let's bring out Ziggy and ask Ziggy to do some work. All right, so I'm going to do a math 9 of the square root of 1 plus 1 divided by e to the 2x, or you could just write e to the negative 2x instead of 1 divided by. Second, e to the 2x, close the e to the, close the radical, comma x, comma 0, comma 1. Did I do anything weird? Questions? So let's see what that is in a fixed 4. I'm in fixed 4, I think. All right, so I get 1.1927. Let's write that down. 1.1927. Now, what's your intuition here? Is this going to be a convergence table, the limit exists? Or this is going to be a divergence table, the limit does not exist? How long is this horn? What's your intuition? You think you're going to get a limit here? The values get closer and closer to something? Or they get farther and farther and farther apart? I think it's a divergence table. Let's find out. How do you find out? Oops. Okay. So what do? All you do is change. I'm going to do second enter, so I don't have to type all that. All you have to do is change the 1 to a 10. And remember, whoops, that's not a 10. Remember that Ziggy automatically puts the last parentheses in there. If it's the last parentheses, you really don't have to write it. If you're missing a parenthesis that's not the last parentheses, it's going to mess everything up. So I usually write it just to be safe, but in this case, I don't think you need it. And boom. Now I get 10.226. Okay. 2260. Let's pretend that there's some kind of 4-place convergence. All right, do it again. Let's see, second, enter, or retype this whole mess, and then type over mode, just type the 0 there, and I don't think you need the parentheses in this case, but play it safe. $100.2260. What's happening? Can you predict what I'm going to get if I plug in 1,000 for B? Yeah. This is not only getting bigger and bigger and bigger, farther and farther apart, but it's predictably so. How big can I make this area? As big as I want. Okay, so that's an indeterminate answer. That's what we call infinity. I don't know what the hell it is. It gets as big as it wants. If I put 1,000 here, it's going to get 1,000 point something. Put 10,000 here, we're going to get 10,000 point something. Probably. Try it. So, this limit does not exist. Right. So I'm going to say, does not exist. So that arc length is infinitely long. It's just too big, too damn long. All right, I need to stop recording at some point. So guess what? This is the point.